This is chapter 4, all about functors. Functors are an abstraction that captures the features of what it means to have container-like types or container-like data. Functors are always type constructors, so they're parameterized by a type. And they mean a container that has items of values of that type. First example would be a sequence. So that is obviously visualized as a container that has 0 or more items of type T. So sequence of T, written like this. But there are other containers like, for example, future of T. And they're very different from sequence. How do we formulate this idea that something is a container, some type constructor represents a container when they're so different? So sequence is one or more values of this type, so you can take one, you can find which one is in the sequence or how many and so on. And here's another one which represents a value of type T that will be available later, or actually may fail to become available. But it's not available now in any case, likely. So how do we abstract away a common feature between these two very different data types? It turns out that the common feature is what I call here the bare functionality of a container. It's just the functionality that describes the idea of holding in some way an item or perhaps several items of type T. And holding means you can manipulate this data inside the container. And that's the only way that we can interpret this. If there is data inside the container, but we can never manipulate it in any way, then that's not reasonable to call that a container. So what does it mean to manipulate? It means we can apply functions to these values. Because in functional programming, that's all we do. We apply functions and get new values out of old ones. So the idea that a container holds items, it means that we can apply a function to these items, and the new items will remain in the container. So we're not extracting items out of it, we're just transforming the items that stay within the container, and that's what it means that the container holds them. So to make it formal, we write a function that takes a container with items of type A. It takes a function of type A to B, and it returns a new container with values of type B, where all the values that were held in the container here have been transformed through this function into values of type B, but they remain in the same container, or it is a new value of a container type, but they remain within the same kind of container, a container of the same shape. So for instance, if it were a sequence, then it will remain a sequence. So we have a sequence of A, we can map and we get a sequence of B. Each value, each data item in the sequence would have been transformed through this function, but the resulting data of type B remain within the sequence, and so it's the same shape of the container that remains, and the data is not extracted out of the container, it remains within the container. And the same thing happens with the future type. You can do a map on a future and transform through a function, and you get a future of B, which means that a value will be available of type A in the future, and once it is available, you will transform it through this transformation and you will get a value of type B also in the future. So this is the common pattern between sequence and future. It's a pattern that allows us to transform data while keeping that data within the same container. So that's what I mean here by the functionality of bare container. So for instance, making a new container out of a given set of data items is not part of that functionality. Or reading values out of the container, or adding more items, or deleting items, these are also not part of the functionality of the bare container. So these are specific containers that we will consider later that can do this. But the most basic and common among all containers is not this, and also not waiting or getting notified when new items become available, like in the future container. None of that is the basic functionality of a container, only this. So if we have the map, then we have a container. We can additionally have other things, and of course any kind of useful container will have other methods and will have other functionality. It is unreasonable to just use bare container. You can't do anything with it. You can't even create it or read values out of it. So in any specific case, you will have a bunch of other methods for any specific container. So for example, if you want to create a future container, it means you need to create some parallel process that will be running and computing this value of type t while you're still doing your computation. So creating a container of this type actually involves creating a parallel process or parallel thread of computation. Creating a container of this type doesn't involve that necessarily. So these are going to be specific things that I'm not going to talk about in this tutorial. I'm only going to talk about what is common to all containers, which is the bare container functionality, which is the map function. So let's consider option as an example, and I will be using this short type notation a lot because it's easier to read and to reason about. So option is defined as this type, as a disjunction of unit and a value of type A. So the map function, if option were to be considered as a container, it needs to have a map function, would have this type. So it goes from 1 plus A to B to 1 plus B. And this function needs to produce a new value of type option B, which possibly contains transformed data. But option could be empty. That's the nature of what the option is. It has two versions, or two parts of the disjunction. One is the empty, and one is the non-empty, where you have a value of type A. So maybe this function will return the empty and lose all this information that was there in the initial value of the option. So how do we avoid that? Is it this function, how do we define this function so that we don't lose information? And how do we also define this function so that it actually allows us to manipulate values? So are there some constraints on this function that we need to be aware of? And that's a center point of this tutorial. So these are the main questions that we will be dealing with. How to define this map function in a sensible and reasonable way, because that's part of the idea of a container, because a container does not lose information. You transform information inside it, but you don't lose it while you're transforming. Losing it would violate the whole idea of having a container that holds information. So the first question about information loss, we will translate that into a formula because we don't want to just talk about some intuition. Intuition is important, but we also want to formulate these both requirements as very precise formulas, as requirements, or as we call them, laws. So here is how I would formulate a requirement that the map does not lose information. If you give it a transformation, so remember the type signature of this function is this, we needed to give it an initial option and a transformation. So if you give it a transformation, which is identity, it means you don't change any data. You don't intend to change any data. You give a transformation that doesn't change anything. You expect that the container will not change, that the new container that you produce out of the map will be exactly the same as the old one. Well, if that were not true, then obviously even doing nothing would lose information or change things in some unpredictable way, and that violates the idea of manipulating values in the container, because manipulating means you apply a function. So if you apply the identity function, it means you didn't do anything. You did not actually intend to change anything, and so that should produce the original value of the option. So this is the law, which is called the identity law for map. And let's apply this law to this case. So actually, if you try to implement this function, there are two ways of implementing it. One would be the reasonable, that is, if, so this is a short notation for code, but you have done this in the Scala exercises in a previous tutorial, so I assume you understand what Scala would be for this. I prefer to write short notation because it's easier to visualize what's going on. So the argument is 1 plus a, so it's either 1 or a. Then another argument is the function f. So if we have a left version, then we return the left. If we have the right version here, then we return f of a. So that is the usual way of implementing map for an option. But the other way would be to always return the left version, the none, or the unit in this disjunction, and never return anything in the right part of the disjunction. So, so basically, yeah, this is, I see there's a little syntax error here. There should be an arrow. I will fix that in the slides after this presentation is over. So, so basically, the second version always loses information. It never takes this a and does anything with it. So even if I give the identity function here, I will still lose this a. So that version has information loss. And we don't want that. So we will prefer the first implementation. Here's a summary of my short code notation, which is that you put type annotations as superscripts and type parameters here in brackets. And you can put also type annotations at the same time as type parameters like you do in Scala. And if you have an argument that is a disjunction and you write it like that, and then you use a and b on the right hand side, and that implicitly should generate some match with cases. On the right hand side, if you want the left part of the either, for instance, then you say a plus 0. So, or you write 0 plus b. So you write the 0 explicitly to indicate that you're returning a disjunction. Just like in Scala, you have to write left, you have to say left explicitly if you're returning a disjunction. And 1 you write for unit value and also for the none value of the option or any other named unit that you have in your disjunction. Now that is something that the previewer does. Sorry about that. Now the second requirement is that we want to be able to manipulate values, and that requirement is about how you would manipulate using different functions. So you apply one function and then you apply another function. So what will happen then? So now to see what happens and to formulate that requirement, which we haven't yet formulated clearly, it's easier to flip the arguments in the type signature of map. And the type signature is that you have the container as the first argument, and that returns a function whose argument is a to b, and that returns a container. So these are the two curried arguments, and if you flip them, and you have a type signature like this, you take a function from a to b, and that returns a function that takes option a and returns option b. So that is denoted Fmap. So you just flip the argument order. There's no change otherwise to what the function does. But it's easier to reason about this function if you flip the arguments, because then it looks like a function from a to b into a function from option a to option b. So this looks like lifting a function from a to b to option a to option b. So from one kind of function space to another kind of function space, you're lifting the function. So that's much more visually clear what this function Fmap does. But for coding, in Scala especially, it's actually easier to use this order of arguments, because you usually have map as a method on a class, so you have a.map of f, and that's also easier to read in code. So you have f dot, some kind of option here, dot map of this, and that returns that. So in this tutorial, however, we will not use methods on classes, because that's actually more advanced from the point of view of functional programming. And the easier thing is to just write a function with arguments. And so our map function will have this form. We'll have one argument, which is a container type, and another argument that's a function type. And the Fmap will have the opposite order of these arguments. So this is what we would write. Fmap applied to a function from a to b returns a function from option a to option b. So after this digression, let's formulate what it means to manipulate values. It means that the functions, when you lift them into the container, behave still like normal functions behave. And that means when you compose them, they have the ordinary properties. And what are these properties? So these properties are written here. If you have a function from a to b, you compose it with identity function, then you get the same function you had before. And you can compose it on the left, and you still have the same function you had before. And then if you compose functions like this, the order of composition, f, g, h being the same, but the order in which you first take this pair or you first take this pair, that doesn't matter. So that's called associativity. So there are these laws, and they should hold for the lifted functions as well. So that's going to be a bit difficult to understand, but actually what we're going to do is we're going to say that, well, we already have the identity law, which was motivated by information loss avoidance, and that requires that Fmap of identity is equal to identity. And so when you lift identity, you get an identity on the lifted type of the container. And so it's reasonable then to require that when you lift a function and you compose it with another function, then the result is going to preserve function composition, so that if you compose two functions and lift them, it's the same as if you first lifted each of them and then composed them. So these functions are composed in the original space, and these two functions after Fmap are composed in the lifted space, in the space of the container values. So if we require this much easier property, then these are going to be automatically satisfied, because these are going to be just composition in the lifted space, in the container space. So these are therefore going to be the laws. Now we can make a definition, write down a definition of what is a functor. So functor is a term which is used in functional programming recently to denote this abstraction of the functionality of a bare container. The bare container having a map with laws. So the definition is that functor, first of all, it is a data type that has a type parameter, such as something like this. Now, if you don't have a type parameter, you cannot have a container, obviously. Or you cannot abstract the functionality of a container if you don't first abstract the type of values to a type parameter. I mean, you can have a sequence of integers and you can say that's a container. It is, but it is not abstracted, and you cannot reason about its properties as an abstract container. And so you cannot see what is common between a sequence of integers and some other sequence, like a sequence of booleans or a sequence of options of some other thing. You cannot see what's common between them unless you abstract the type into a type parameter. And so the abstraction for this functionality requires you first to do that, to have a type parameter. Second requirement is that a function map should be available for this data type with this type signature, or Fmap. These are equivalent. They just differ by order, or the order of curried arguments. And these functions must be such that the laws of identity and the laws of composition must hold. So these laws are written like that. In terms of Fmap, is much easier to write them, shorter, and also easier to see what these laws do and to remember why you need them. And of course to check them. So the Fmap applied to the same type A and A, identity A or A gives you identity FA to FA, and Fmap applied to a composition of functions gives you a composition of lifted functions. And so now I just want to mention that the word functor comes from category theory. It is not going to be useful for us to go into category theory right now, but there is different usage of the word functor in programming or in software engineering, which are not the same as what we're doing here, which do not come from category theory. So for example, even C++ now has something called a functor, and OCaml has some other thing called a functor. These are not the same, and this is just a very specific usage of the word functor that is now being dominated, the dominant one in functional programming. So this functor is a concept from category theory and not something else. But for us, this is not very important that it comes from category theory, because we are actually motivating these laws by requirements of practical use. So you want to manipulate data in a container, and if you want to do that in a reasonable way and be able to understand your code after you have written it several years back, then there shouldn't be surprises. So if you, for example, identity law just tells you that if you manipulate data by doing nothing, it shouldn't change your container. So it would be very surprising in your code if that were the case, and you would never find the bug until you debug every step painfully. And so that's the kind of thing we want to avoid by imposing these laws. And the second law, the composition law, also says that basically functions are applied in the way you expect them to be applied, and there's no surprises. So you can simplify your code. For instance, if you discover that this function g is identity, you can omit it from the code, and the code will still be working. And that's not the case if this law is violated. So let us go to actual code demonstration to verify the laws for the option. The Fmap implementation for the option is written here. It's a very easy thing that you take a function f as a parameter, and you return a function from option A to option B. So now, if you return a function like this, an option is a case class or a sealed trait with case classes, or disjunction, as I prefer to call them, then a short syntax in Scala is to just write a case partial function with case. So you do not say much more than this. It's just very easy to write that. It's a shorter syntax. And then if the option A is empty, then you return none. And if the option A is not empty, then you return a non-empty option B with the value inside that is transformed. So let's go to the code. So this is the code that is written a little more verbosely. And there are three versions here. Well, first of all, I do the map, not just the Fmap. So the map takes an option A, takes a function A to B, and returns an option B. And so since there's this syntax, I have to say the first argument is this opt, this is the option A. The second argument is F. So let me check the types. Control-Shift-P. So option A is being matched, and then if it's non-empty, we return this. It's empty, return that. Now the bad implementation would be if we did the same thing, but we always returned none. So that would be a bad implementation that doesn't satisfy the laws. And the Fmap is exactly what was, well, basically what was written there, except for the F being here, just a syntax difference. And I also have a fourth implementation, which is Fmap auto, which is automatically implemented. So I'm using, this is the function from the Curry-Howard library, which I'm using here just as a reference check to see whether these methods can be automatically implemented or not. So then we verify the identity law for all these implementations. So this is the way to verify the laws is to use the Scala check library that allows you to say things like this: for all value of option int, this must be true. And I just write here what I want to be true. Like, for example, here, the map, which I defined right there, applied to this option and to the identity function should be equal to that option. So that is my statement that identity being lifted is equal to identity. But I cannot compare functions directly in Scala. I have to say for all argument opt, the function applied to the argument is equal to the argument. That's the only way I can say that the function is equal to identity. The library Scala check will go through a large number of randomly chosen values of this type, and it can generate these values automatically. The checking for Fmap is quite similar, except for the order of arguments, which is inverted as compared with Fmap. And Fmap auto, exactly the same as Fmap. Now, for map bad, actually the test would fail. If I wrote the same test for map bad, it would have failed. Because map bad does not give you identity. It always maps your option to none. So if once you take here an option that's not none, you get an error. And also we verify the composition law. Which means we say for all x and for all functions f and g, and here I chose some specific types like integer, string, and long. All our functions here are completely type parametric, so I can say any types I want, but when I test, I have to give a specific type because there will be specific values randomly generated for these functions, and it is impossible to do that unless you specify a type. So you have to choose, and I choose some random different types. So then here's how I check the composition law. The and then is a standard Scala function, or method rather, that is defined on functions. So f and then g means that the same as you would write this circle in my slides. The composition is a circle. It's in Scala will be and then. So first a and then b. So sorry, first f and then g. So if you apply this to a value of type a, then first f will map it to b, and then g will map it to c. So then it's easier to read it that way. So there's this. So basically I write down this law as written here, putting and then instead of the circle. Fmap f and then g, Fmap f and then Fmap g. And then I also have to apply the resulting function to an x. And then I say that the result should be equal to applying the other function to the same x. And that's the only way to check that functions are equal. Here, this is the equality of functions. This lifted function should be equal to that lifted function. And in the test, you cannot directly compare functions. You have to apply functions to values and say that for all values, the results are the same. So that's what I do. And again, I have a check for all the implementations, including the bad one, for which the composition law actually holds, because this thing always gives you none. So whatever you compose with, the result is going to be none in any case. And so the composition law will trivially hold, but the identity law does not hold. Here are some examples of functors. So like I said, we are only concerned about the properties of map here, and all these specific examples will have lots of different other methods so that you can do other things. So for example, option T has methods to get values out of it and to put values in it and so on. So basically anything in the Scala standard library that has a map method is a functor, except for set and map, which are almost functors, except that for certain not well-behaved types, the laws will not hold. let's see how that works. So here's some example. So have a I took this idea from here, from Rob Norris. So imagine we have a type bad, which holds an integer, but it has the equals function that is not well behaved. The equals function always returns true for any other thing, which would be kind of unreasonable and useless. But what if this was true for some reason? What if you need this behavior? Then you define a function f and a function g in a very obvious way. You take an integer, you put it into the container. So this can be seen as a container itself that contains a single integer, but we're not using that as a container. We're using that as a data type inside the container. So you put an integer in there in the obvious way, and you get the integer back in the obvious way. So there are two functions, f and g. And now let's take a set of integers and map with the composition of these two functions. And so then we write it like this. So you see in Scholar it's much easier to use map rather than fmap because of the syntax. So then you get this set, because f and then g is identity. Because you take the f, you put an integer inside, and you get that integer back with no changes. You're not comparing anything while you're doing this, and so this function is identity, and of course the set does not change when you map it over identity. But if you first map into f and then map into g, which you expect to be the same as that, then you get a wrong answer. Because when you first map it through f, then it becomes a set of bad 1, bad 2, bad 3, and then the set tries to see if they're equal. Because a set is trying to eliminate duplications, right? Because a set cannot have duplicate elements. But we have made the equals operation so that it always returns true. And so the set will think that all of them are the same, and it will eliminate all of them except the first one, perhaps. And then you map it back to integer, and you get a set of one element. So the composition law fails. And that's bad. So basically, for a set of integers, it is not true. Or even set of integers is a well-behaved equality operation, but because you go through some bad type while you're composing functions, you are violating the composition law. And the map is similar. It has a map values method, which is a good functor, but it also has a map method, which is the mapping with respect to both key and value, and it behaves like a set with respect to keys because it will not allow you to have duplicate key, and that's the same problem as with the set. So if you have a map and you have functions that map you to a type with an ill-behaved equals operation, then you will violate the composition law, and that code could have difficult to find bugs. It will be very difficult to reason about that code. So that's the real value of these laws. I would like to have a little more intuition about functors and type constructors in general. And a good way, rather than look at some types defined in the standard library, which are complicated, let's look at very simple types that we can define ourselves and work with ourselves to understand how functors work and what it means to be a bare container, what it means to be a functor. So here I have three examples. First example is a type query result. parameterized by a, the type variable a, and it holds a triple of string, integer, and a. So the short notation for this type is this, and the Scala code would be that. I have to put names on each, so I'm just writing down whatever comes to mind, what would be appropriate for a query result. And another example would be a vector in 3 dimensions having coordinates of type A. So you have 3 coordinates of type A. So A could be maybe double or real or complex or something like that. 3-dimensional vector of type A with coordinates of type A. And the third example would be a disjunction type, a query result that could be, so the short notation is string plus string times integer times a. In Scala code, that would be a sealed trait with 2 cases, so I'm just interpreting what it could be. So one could be an error with a message, and another would be a success with a value of type A. So see, the first element of the disjunction does not actually contain any elements of type A, any values of type A. The second one does. So let's look at the test code to see how we make them into functors. So the first example was the string times integer times a. So we need to define Fmap. In all these examples, we will be dealing with Fmap because it's much easier to write down, but map would be equivalent in code. So to implement Fmap, what do we do? Well, we need to take, given a function f, take a query result of type A and return a query result of type B. Now, I could have written this as that, because what I need here is I need to return a function with argument of type query result A. So if I need to return a function, then my code needs to start like this. This would be the argument of that function, and that would be the result value. Now, the first thing I have to do is to match on this query result, because it's the easiest way to extract values from it would be to match. And then I would say case query result with 3 parts, and then I return query result with the same parts, except I apply the function f to the data. So you see, I need to transform string times integer times a into string times integer times b, and I have a function from a to b. The only way I can do it is to apply that function to the a and leave the string and integer unchanged. And that's the code I have written here. And this is a simplification of syntax, so that this is not necessary to write. Otherwise, it's exactly the same code. It is a function that takes an argument of this type, immediately does a match on that argument, and returns this. An equivalent way of writing this code would be like this. So you take this argument, and you use the copy function on case classes that copies so it copies the entire value of the case class, and it only changes one part of it, which is data. The new value is equal to this, f of the old qr.data. So in this case, because the code is so simple, the case match would be a lot more writing than this. In every other way, these are equivalent. I'm creating a new value of type query result b, and I'm copying all the parts, name and time, and I'm only modifying the data part in this way. And I can do this automatically using the Curry-Howard library. So that's the last implementation. And I verify identity law and composition law for all three implementations. The second example was the type constructor that has a triple, a three-dimensional vector of A's. So here I do the same thing. I do a case match on the vector, and now I have to apply the function f to all three of the elements here. So again, I've tried the automatic implementation, but actually there are different ways of implementing this automatically, because you could, for example, you could interchange x and y here. So the type would still be correct. And the automatic implementation only looks at the type and tries to find out what code could be of this type. Now, if I wrote here y and x instead of x and y, the type would still be correct. The functor would be incorrect, as we will see later. The composition law will not hold, and the identity law will not hold. No, it's obvious that identity law will not hold, because if f is identity, then you're exchanging y and x. You're not leaving the vector 3 unchanged. But the Curry-Howard library doesn't know that we want to have the identity law, and so it only looks at the type, and the type would be correct. So then there are 6 different ways of permuting the order of these, and it finds all 6 and has no idea what to choose. So as a workaround, I say, give me all of those implementations and take the first of them. And actually, it turns out to be the right one. So all of type returns a sequence of values of this type. And I check the identity law and the composition law, and all these tests pass. And the final example right now is to make this into a functor, to define a map for it and check the laws. So again, this is very similar to what we had before, except now we have 2 cases of the disjunction. In order to transform this into the clear result of B, we still just need to apply f to this A and get a B, and we're done. But now there are 2 cases. In the first case, we actually don't have any values of type A, we just have a string. And in the other case, we have a string, an int, and an A. So we need to do a case match. So here's how we define it. If it's an error, so you see there are 2 cases, error and success. If it's an error, then we just return error with no change to the message. And if it's a success, then we do what we did before. We apply f to data and leave other parts of the case class unchanged. And the Curry-Howard library can implement this automatically. There's no uncertainty as to what to do. Only one good implementation. So that's these 3 examples. In these 3 examples, what we found is that we can define Fmap. So we try to define Fmap guided by types and also guided by laws. So sometimes we have different possibilities for the same type to write code, but the laws only leave us one possibility. And that's the general situation with all the type constructors that we are going to work with. Laws and type dictate how to implement map in only one way. What are examples that are not functors, where you cannot implement map? Well, one type of these examples is types that cannot have any map function at all due to type problems. An easy example is a not container, which is defined as a product of a function from a to int and a. So the case class would be like this. So you have a function from a to int and also a value of type a. So why is this not a container? Well, we can try to implement map for it, but that won't satisfy the law. I mean, what it would do is it would transform the y, and then it would apply that function to that a that you had and get an integer. And you cannot produce a function from b to integer, but you can produce a function that's returning you a constant integer. And so that, because you have an integer, you can compute a constant integer by applying x to y. And so you just return a constant function that always returns that constant integer. Now that is not the right implementation for Fmap because it doesn't satisfy the laws, which I check here. So I check that the try Fmaps that I get here does not satisfy identity law. Another example of a data type that cannot have a map due to type problems is this one, where you have a disjunction type, but its type values are non-parametric in some strange way. So here's what I mean by that. You have a sealed trait with a type parameter called res, so it's some kind of action with results, let's say. And the case classes that extend this trait are defined in this curious way. So the first one is normal. It has a value, and it extends the survey action with the same type parameter res. But the second case class doesn't have a type parameter and extends survey action with a specific type long. And also the third case class extends that with specific type string. So it uses type values that are not parametric, type values that are not equal to this parameter. So the way that we have case classes for option or either or such parametric disjunction types is that each case class extends the trait with the same type parameter as it has. And here it's not the case. It extends with a fixed type. So these kind of disjunction types are called generalized algebraic data types. And I don't have short notation for them that's very useful. And at this point, I'm not sure what that short notation should be and how to reason about them in terms of data containers, because they are not data containers. They're very odd type constructors if you try to think about them as containers. They may be very useful, certainly are very useful in a number of situations, but as containers they fail. You cannot even implement Fmap or map for this, because you do not actually have a value, let's say server action long or server action integer for this. There's no, if you want to have a function that maps long to integer, you cannot do a store ID server action integer because that's a fixed type. So there's no way you can define map for this kind of type because of type problems. Another type of things that are not functors are types that could be functors, but we didn't implement map correctly. We need to have a well-behaved Fmap to have a functor, and a number of things could go wrong if we try to implement Fmap. So one thing could be that Fmap ignores f. It always returns none for an option. So for instance, if that is true, usually it would not be satisfying laws. Or Fmap reorders data in a container. For instance, here's a container with two values of type A, and we define Fmap that applies f, but also reorders the values in the container. Now this, or here is this example I was showing in the code. Now this would immediately violate the identity law. So that's not good. And we can verify that. So we can have tests with this special method existSum that I implemented. We can verify that the identity law is not satisfied. Another example is that you could have an Fmap that checks the types, because in Scala you can see what type you're passed using reflection, and that's a very risky thing to do, because it's easy to make mistakes and difficult to write code that will always work. But if you do that, you could check that A and B are the same type or not, and if they're the same type, then you do one thing in your Fmap. Let's say you return identity ignoring the f, and if you have another not the same type, then you do something else. You apply f of x in some way. Now this would obviously satisfy the identity law, but this would violate the composition law, because you could have functions f and g whose composition is identity, and so then you would check that the type is the same, and you would, sorry, whose composition is not identity, and you would check here that the type is the same. You would return identity for them, and it would not be equal to the composition of f and g. So you would violate the composition law if you do that. Or you could do other special computations in case that the type is equal to some specific type, like integer, then you do something else than in the general case. Or if the function is equal to some specific function, then you do a special thing, and otherwise you do the general case. So none of this would give you an Fmap that's well behaved, that satisfies the laws. So an interesting example of functor is a recursive type defined like this, for example. So let's say a list of pairs, which I could just define by hand, as a type LP with parameter a that satisfies this recursive equation. This is a type equation. LP of a is equal to 1 plus a times LP of a. So if you expand this using the algebraic or arithmetic Curry-Howard correspondence rules, the arithmetic identity would be this kind of expansion. So then you can visualize what this type does. So it's either empty, or it's two copies of, two values of type A, or 4 values of type A, or more. So it's kind of list of pairs, except it's a list that can only have an even number of elements. It's not really a list of pairs as I've defined it. So here's a definition in Scala. So you have a seal trait LP of A, and it has two parts of the disjunction. So one, I would write it like this, with empty or unit here, and the other with x and y of type A, and the tail, which is this, which is again of type LP of A. So that is allowed. So this kind of type recursion is allowed in Scala when you do when you use case classes. So now we can implement map here if we use recursion. So let's implement fmap for simplicity. You match on LP of A, and there are two cases. So either it's empty, and the result will be also empty, or it's going to be a pair of x, y tail, and then you apply f to x, apply f to f to y, and you apply f to tail. Now tail is of the same type, and so you need to use the same fmap. This should be an fmap here. Should the same fmap that you're defining, this you use the same recursive call here, applying to the tail. So that's all right, and that works. And actually, this is the only way to implement map that satisfies the functor laws. What would be another way? Well, we could always return empty here. Or we could match on this tail further, and let's say if there are at least 4 of them, then we return empty. If there's not 4, we don't return empty, or something like this. All of that would be wrong. All of that would be incorrect functor instance, as it's called, incorrect implementation of map. So let's look at the test code. So here's the implementation of this. Recursive type is defined like that. So here I don't have this typo, obviously, because tests pass. They wouldn't compile if I made the typo. So that's now for this example. It's exactly the same code as before, verifying the laws. Now notice that I'm able to generate arbitrary values of this recursive type. So how does the library do it? Just a short digression. I'm using a library called Scala Check Shapeless, which is a library made by Alexandre Archambault, and he allows me to use case classes in for all. So I can do for all value of some case class or sealed trait. And I don't have to write any code to do that. It's automatic. So this is some macro and library that I'm using. Now, another curious thing is that a type such as this one, a function from A to int, is not a functor. You cannot implement map for it, but you can implement something called contramap, or here contra fmap, which is similar to fmap, except that I interchange the order of B and A here. So the function goes from B to A, but the lifted function goes from CA to CB. So that's the contra. It reverses the arrow between A and B. The contrafunctor laws are very similar to functor laws, except for the interchanging of the order of the function here in composition. So this is the contra direction. So composition G and F, and that's composition of F lifted and G lifted. An interesting observation here is that in this type, the type parameter is to the left of the function arrow. So this type parameter A is consumed by the function. In all our examples of functors here, this was not the case. The type A was produced, or it was there. It was not consumed. here it was consumed in all these examples of functor. So that was an example of a non-functor. And all of these examples, they have a that is produced, or it's already there, but it is not consumed. So that's an interesting observation. That functors contain data, but contrafunctors consume data. So contrafunctor is not a container, is not a functor. So it's not a container, it should be thought of as a container. It's something that consumes data of this type. This is an example that we had before, the non-container. It is neither a functor nor a contrafunctor. So I have here some test code. I tried to implement contra Fmaps for this type, but actually there aren't any implementations. There's 0 implementations possible. There's one implementation possible of the Fmap, but it does not satisfy the law. And there are no implementations of this type at all. So this type is neither a functor nor a contrafunctor. So it cannot be thought of as a container, and also cannot be thought of as something that consumes the data of this type. It's a strange thing, maybe useful, maybe not, but in any case, it's not a functor and not a contrafunctor. So now that we see functors and contrafunctors, another thing that comes to mind is the concepts of covariance and contravariance. Now the concepts of covariance and contravariance are relevant to subtyping. So what is subtyping? An example would be when you say class extends something, trait. So in Scala these are traits, and classes, these is a bit specific to Scala, so in other languages would not be called traits maybe, and would be just classes, but this is a subtype. So 0 is a subtype of at most 2. So this is an example where I have at most 2 is a disjunction of 0 integers, 1 integer, or 2 integers. And so the 0, 1, and 2 in Scala are types themselves that are subtypes of at most 2, which means that if you have a function that takes an at most 2 as an argument, you can pass this value to that function, and it will take it. So this is how we have been using disjunctions until now. So we're using this feature of Scala that they're implemented as subtypes, and subtype means that you can automatically convert this type into that type whenever you need that. So this function going from 2 to at most 2 is identity function. It just relabels the type because there's nothing to convert in this case. This class is just an instance or a subtype of that. So, but logically speaking, they're different types. So this type is different from this. And so you can think about it as having always an automatic type conversion of this sort whenever you need it. And so this looks like a function of this type that's always available. It's never need to be written out explicitly. But we could write it out explicitly if we wanted to. And we will in a second. So what does it mean that a type constructor is covariant? So it means that if the container or type constructor applied to the type 2 is a subtype of the container of at most 2. In other words, when you lift these types into the container type, they still are subtypes of each other. So this 2 is a subtype of at most 2, and then C of 2 is also a subtype of C at most 2. If that is so, then C is called covariant. And then you have this type conversion function automatically available whenever you need it. So more generally, what is covariance? So covariant So C is covariant, type constructor C is covariant in its argument X whenever if you have X is a subtype of Y, then you have also this conversion automatically. And obviously, if you have this kind of function, which is taking this and producing that, if you have this kind of function, then you're guaranteed to have this kind of conversion. In other words, and this is the type signature of Fmap. In other words, if you have a type constructor that has Fmap, then it's guaranteed to have the right type conversions and to be covariant. And so all functors are covariant. And in Scala, you can put the little plus next to the type when you declare the sealed trait to tell the compiler that you want this explicitly to be known that this is covariant in that argument. And similarly, contrafunctors are contravariant. So contravariant means that this arrow goes into the opposite direction. If 2 is a subtype of at most 2, then a contrafunctor of at most 2 will be a subtype of a contrafunctor of 2. And so, because of this very easy argument with the implicit or automatic type conversion functions, if we write them explicitly, then we see immediately that functors are automatically covariant and contrafunctors are automatically contravariant. So if you want to make this explicit in Scala, if for any reason you need subtyping, which is an advanced topic in functional programming, and it's not something I'm going to talk about a lot right now, you can put a plus sign or a minus sign for contravariant, and then the compiler will check that you actually have covariance or contravariance correct. So this is the correspondence between functors, contrafunctors, covariance, and contravariance, which is a very interesting thing. So in other words, we are talking about functors and contrafunctors, and this is exactly parallel to covariance and contravariance that usually in object-oriented programming people talk about. So let's go through some more examples with actual coding, where we will do certain things. We will first, we can now decide if a data type is a functor, a contrafunctor, or neither of these two. So to decide that, we look at the data type, write it down in the short notation, and see if there is any type parameter to the left of the arrow which is consumed, and to the right of the arrow or without an arrow which is either produced or which is already there. And that allows us to decide whether it's a functor or a contrafunctor. Then we implement a map or contramap that satisfies the laws. So we are implementing, first looking at the type, just guided by what types need to be produced. And if there's any choice or ambiguity, we then see whether laws are satisfied. So let's look at the first example, which is this one. So we have this type, string plus a times int plus a times a times a. Our task is to define case classes for this type and implement map. So this is how we would write the case classes. In all these examples, I'm going to call this type data, so that all my code is always ready to cut and paste. So in this case, we have three pieces of the disjunction, or disjunction. So there are three parts of the disjunction. The first part is just string. So we have this. The second part is a product of a and int. So we have our tuple. We have a and we have an int. And the third part is a. So Fmap makes a match on the data disjunction. If I have a message, then I don't change that message. Now, in any case, I couldn't do anything else at this point. I have to return a message of type B because there's nothing else I could possibly return. If I have a second case class, then it means I have one item of type A. So then I apply f to that item and I'm done. And the third case, I have three items of type A and I apply f on each of them and I don't change the order. So that's how I would implement it. The second example is this one. So now in this example, first what I notice is that I have a type of the form 1 plus something. So in Scala, I already have option type. So I don't have to myself implement the cases for that. So let me use it. So it will be an option of this. And that is a tuple of A and disjunction. So for this disjunction here, I declare another sealed trait, which is called data2. And here, this trait is still parameterized by A. It has two cases, the message and the value. So now I have a bit more complication in my code, because when I match on data, then that's a case class, so it has a data constructor over option. So it's a data of option. And the option needs to be matched as well. So I can match this in the same case expression. And I have two possibilities, data of sum of blah and data of none. Now, if I have data of none, then clearly all I can do is return data of none. There's nothing else I can do. I couldn't possibly return any of those things. So it remains to do this with the case data of sum, and the sum is of a tuple, of a pair, more precisely, of A and this data 2. So there's a pair of value A and data 2. So then I'm going to return a data of sum of some new value A and some new data 2. So I'm going to return this. And in order to make the code more readable, I'm going to write explicitly what new value A is and what new data 2 is. So new value A is just a function f of the old value A. So in order to make this more visual, in my head I do this, but maybe for tutorial purposes, let me write this out. This is what I want to do. I want to transform data A into data B using this function f. So I need to replace A by B exactly at each place that I have A. Here I replace it by B, and replacing by B means I apply f to that value A. So then all I need to do is I need to case match, and whenever I get a value of A, I apply f to it. Here I have another value of A. Control-Shift-P. That's A. I apply f to it. Everything else I don't touch, so I don't change these integers, this string, I don't change the order of anything. I just replace A by B by using the function f, and change nothing else. So this one goes to this one, so that's this line. This A goes to this B, that's this line. Integer string goes to integer string, that's this line. And this A goes to this B, that's that line. So that's all I'm doing. And of course the laws will hold then. The third example is a bit more involved. In this example, I notice first of all, the structure of the data must be that first it's a disjunction of two parts, and the parts are quite similar. So each part has this structure that I have string to integer to A, here I have boolean to double to A. Other than that, they're and times A, so that's always a tuple with A. Except for these types boolean and double, it's exactly the same structure. So I'm going to parameterize boolean and so on by xy, and I'm going to define a structure like this, and that's going to be data2. So it's going to be a case class with two parts, so that, or a tuple with two parts, and I'm going to do x and y setting them to string int here and to boolean double here. So then I define not a case class but a type. I don't have to do the case class if I can. Well, I already have either as a case class, and so that's actually a little less writing than what I was doing in the previous example, where I could also use either or a tuple here, but I chose to do, here I chose a tuple, then I chose this data2 that explicitly had two cases, but I could have used either and tuples and just write all of this as one expression with either and tuples. I could have done that too. Just a little less writing, perhaps. At certain points could be more writing. So this is not clear how best to arrange this. You have a choice. And so let me try it this way. Of course, all these types are going to be equivalent. They're going to be isomorphic. No matter what I do, I can put them inside a case class or not. It's just going to be more wrapping if I put them more into case classes. So let me try without a case class at this level, but I do have a case class for this repeating structure that I found. Maybe that's also in Scala that's easier to read, because you can have documentation, so to speak, as the name of your data type and names of your elements. They could tell the programmer what they mean, so that it's clearer what needs to do what. In this case, for this example, I'm just using very short names like dA is a data of type A, or G, just a function of whatever kind. So I define the data like this, just an either of two of two data2 structures, and that's precisely mirrors what I have here. So that's Scala syntax for the same. I also need to define a function that compares values of this type. That is necessary because, as you remember, functions cannot be compared directly in Scala, and we will have to compare things in this test if we want to verify laws. So we don't need to compare values of this type. So for example, if something is an identity function, data2 going to data2, and I want to verify that, then I need to compare the data2 that I had before, applying that function, and after. And so that's why I need to have a method of comparing two values of data, of type data A. So that is implemented in the same way, using case matches, and certain parts should be equal to certain other parts, and if not, then I have this special method called fail that will throw an exception. So you can look at that code. So here's how I would implement Fmap. So data of type A is an either. So first of all, I match on that and I get two cases, left and right. Now if I'm in the left case, it means I have a data2 of this type, string int b. And so string int a. So I compute a new string int b out of that. And I return the left of that. And if I'm on the right, then I compute the new data2 and I return that. So now the only non-trivial part is what to do with this higher order function, x to y to a. So I need to transform x to y to a into x to y to b. So how do I do that? Well, I do that here in line, but I could have done it as another val if I wanted to. Like, for example, new g. I could have done that. Let me see if that would be perhaps more instructive. So what is the type of new g? I need to specify the type, otherwise it cannot be derived in Scala. So I need a function from string to int to b. So how can I make this function? I have a function g, which is of type string to int to a, and I have a function f from a to b. So how do I put this new b here? Well, new g is a function, so let me return a function. So it takes x, returns a function that takes y, and then I need to produce a b. So how do I produce a b? I have an x and y. I can put those x and y into g, which is string to int to a, which would be this. So that's the value of type A. Then I apply f to it, I get a b. And that's what I return. So in this way, I can implement the Fmap for my type. So notice this kind of trick with first taking arguments out and then putting them back in. That is necessary whenever you have a type of this sort, which produces a value of your interesting type using some other values. You have to do this kind of code. But this code is actually, this code could be generated automatically. If I wanted to be clever here and use my Curry-Howard library, I could have done like this. And I need to specify what values I'm allowed to use. So I'm allowed to use f and g. So let me do an import so that I have this of type. Let me just import everything. Right. So now of type works. So of type is an interface to the Curry-Howard library that automatically generates expressions of a given type using other expressions that are already available. So it will find that code, basically this code, will be generated automatically. There's no other way of generating this. Let me run this test, and I'll see if that actually works. But I expect this to work, because there's no other way. So this combination, x to y to f of g x y, is the only combination that has the right type. And so should be able to derive this automatically. But of course, it's important to understand how to write this code by hand as well. Only then you can correctly use automatic tools. All right, there's some warning, but warning is expected. The test should pass. Warnings are fine. Oh, actually, it's compiling the first tests still. Right, that will take a long time. It's not compiling this test. The Curry Howard library is used in the first one several times, and it's slow because it goes through different combinations to find this expression. All right, looks like we're compiled. And once we compile, we're pretty much guaranteed to work. Excellent. So we have just checked that all these laws work. The second series of examples is to decide whether these are functors or contrafunctors, and then implement either Fmap or contra Fmap as appropriate. The first example is this type. So now, if you look at this type, here A is on the left of the arrow. So that looks like it's consuming an A. So it looks like we're having a contrafunctor here. Certainly not a functor. Now here, are we consuming an A or are we producing an A? Now this syntax might be a little confusing until you get used to it, but all these things are to the left of the arrow. So these are, the syntax is like this. By convention, the arrow associates to the right. And so this consumes an A and produces a function that again consumes an A and produces a string. So this function actually consumes two different values of A, of type A. And so all of this consumes A. This also consumes two different values of type A. And so we have a hope of getting a contrafunctor here. It's certainly not a functor. Let's try the contrafunctor. So here I'm going to do go with the easier route. I won't define any case classes. I'll just use standard library. So I have a single disjunction. I'll just use either, and then I'll just write down these types, more or less like in this formula. I also define the data equal function. Otherwise, these tests won't run because data contains functions. So whenever that is so, I need to define for these tests a function that will compare for equality. So then I define contra Fmap. So how do I do that? It's a very similar trick as what we did before. We just need to replace arguments here in functions by our own arguments, and that will be it. So here's contra Fmap. We have an either. Our data type is an either, so we need a case match first of all. The left is a function from A to int. So now we need to produce, let me just write down again for convenience, what we want to produce is this. So we want to produce a data B, so if we are in the left, then we should produce this. And if we're in the right, then we should produce this. So if we're in the left, then we produce left of a function that takes some value. It's A, let's call this B, because that's the type. It's more clear. it's a function that takes b and returns an integer. So we take a b, now we need to return an integer. So how do we return an integer? We can do f of b, and we get an a. And then we apply this function, a to integer, to that a, and we get an integer. So that's how we can do this. And very similarly, we do in the right. So there's an a and string. Now this b actually is the first a. Let's call it a1. And this, let's call it a2, just to be more clear. So a1 and a2 are of type b. Sorry, let's call them b1 and b2. b1 and b2. Right. So they're of type b, so we are supposed to produce a function from b to string. So we produce a function, takes b1, takes b2, and then we produce a string. So we get this applied to an a, and again applied to an a. So that's all we do here. So the f of b1 is an a, f of b2 is again a. Now an interesting question is, what order should this be? Should this be b2, b1, or b1, b2? Well, let's see. So this, we just ran tests. Actually, we didn't run this test. Let's run this test. And I think the test would fail if we do it the wrong way. So let me run this test first, and then make a change, and then run the test again. The reason is that we shouldn't interchange the order of arguments. So if we give these two arguments, we should not interchange them. That would probably violate the identity law if we did interchange them. So let me do the bad thing and run the test again. So as a rule of thumb, when we build Fmap code for some data type, we just change every instance of A to instance of B, or vice versa. We don't change any order of anything. We don't, yeah, it fails. Wrong. So there's some values that don't match. Let's see. Identity law. Yes, the identity law failed to hold. So let me undo this damage. Yeah, so as a rule of thumb, never change order of anything, never interchange things. That would violate the laws. And the type would be correct, but that would violate the laws. And so, since here we're implementing a contrafunctor, it could be a bit difficult to decide whether this should be b2, b1, or b1, b2. What is the order of these arguments, really? Just run the tests and make your laws testable. And you are sure to be... there's not much choice here. There are these choices when you have different values of the same type, or different arguments of the same type, then you might, by mistake, interchange them. The laws would tell you that this is not so. This is not right. And the contracomposition law, remember there was a compose of f with g lifted is equal to compose of g and then f. So that's contracomposition. A second example is this type. So it has two parameters, A and B. So which should we use as a type parameter? Now, it's important to realize that we are free to use either of these two type parameters. A functor is a type constructor with a type parameter, but if we have a type constructor that has many type parameters, we need to choose one and say that this type constructor is a functor with respect to that type parameter. And our Fmap will modify that type parameter only and not others. And so in this example, it shows we can choose that, for example, A is our type parameter and B is just a fixed type. I'm not going to, Fmap is not going to change that. Let's examine this type. So there is this arrow here, and this arrow, okay, so it looks like A is behind an arrow. So does it look like A is actually contravariant? But wait, here's another arrow. So this entire thing is to the left of an arrow. So this is, the entire thing is consumed. So we consume something that consumes A. So that actually makes A covariant again, as we will see. If you consume something that consumes A, then you can implement Fmap with respect to A and not the contramap. So it looks like you're not, this is a strange container if it doesn't actually have values of type A, but instead it consumes something that consumes a value of type A. But that is actually, so in other words, you don't have a value of type A. That is true, and not all containers have actual values of type A inside. But one example of that would be the future container. Future is a functor, but it doesn't actually have a value inside. Not yet in any case. It might have it in the future, or might not at all. So that's an example of a container that is a functor with respect to A, but it does this funny thing of it consumes a function that consumes A. Also, B is in a covariant position. Here we have a B inside of this disjunction, and here we produce a B. So we know that when we produce a B, that's covariant. And when, so again, B could be a type parameter we choose to have a functor instance. Or a functor instance is the same as to say we have an implementation of Fmap. So in this code, I will actually define both Fmap with respect to A and Fmap with respect to B. So let me start with B. It's a little easier. So in order to have an Fmap with respect to B, I'm going to put the first parameter, rename it to Z. So let's rename that to Z. Then Fmap will have to be parameterized by Z and B and C, and it will map B to C, and the result will be mapping from data ZB into the data ZC. So that's, I chose the letter Z far from B and C so that it's clear that Z is not changing, B is changing to C after Fmap. All right, so how do we do that? So we again need to think. So this is this case class. There's no disjunction at the top. There is a disjunction inside. So we need to get the data. Data.ab will be matched. The result will be that we need to return a new value of type data, which means we need to produce some new AB and some new D, right? So data has AB and it has a D. We need to produce new AB and new D. So I have structured the code like this to be more clear about that. And now we need to produce a new AB of this type and new D of this type. So how do we do that? So new AB is just an either of these C, so we just need to map over the either somehow. So that's easy to do. If we're in the left, we don't map because it's an A, so that's, or Z, so that's not mapped, not changed. And the B value is mapped with F, so it's changed. It remains to do this. So that's the trick we just saw. This is not changing. And we have a D, which is data.d, which is of type z to integer to b. So we put an argument out, which is z to integer, and apply this d to that. The result is a value of b. We apply f to that value, we get a value of c. So then we get a function from g to that c, and that's what we need, this function. So, like before, this part of code is probably unique. It can be generated automatically. So I haven't tried to actually generate all of this automatically with Curry-Howard, but you could try to see. Maybe in this case there are no ambiguities, and you could just generate all of this code automatically. In which case we just say def fmap of all this equals implement. You can just say that, maybe. Like this. Let's run this test to see if that is so, and I will explain the rest. Now the fmap here is with respect to A. So A is changing, so I rename that into X, just so that it's clear. We are going to map data XB into data YB. So B is the type parameter that remains constant, and we're mapping X to Y through the function X. All right, there's some problem. Okay, doesn't work. There might be a bug, or there might be some other problem, but the Curry-Howard library is work in progress, so it works in many cases, but not in all cases. I'll make a note of this. It's a good idea to have some more tests or bug fixes. So, to implement fmap, we do a very similar thing. We match on data. So, sorry, we return the data with new AB and new D. But now the types of new AB are different. So this is going to be either of YB, and this is going to be this. So the either is dealt with in the same way as before, matching an A or an B. So B is unchanged, and A value is actually of type X now. So we could rename this for clarity into X value. And we could rename this. This is of type B, of type Y, so we can rename this into Y value. Oh no, this is of B. Spoke too soon. Now, what do we do with this? How do we map X to int to B into Y to int to B? So this is the non-trivial part, where we have something. Data.d is X to int to B, which consumes a function that consumes X, and we need to produce a function that consumes a function that produces Y. How do we do that? Well, we just write the code directed by type. So this is a function, so G is type Y to int. Data.d has the type of x to int to b. So we need to use data.d on a function that takes x and produces int. So how do we produce int? Well, the only way to produce an int is to get g acting on some y. So g of something. So this something must be some y. The only way to get a y is to apply f to x. So this code could be generated automatically. Even if that whole thing didn't work, I'm pretty sure this would have worked. If I just say of type here, and I put g and f and data.d. Data g and f. Let me try. So I need f, g, actually f and data. There's no g. And I say of type, and I copy this type expression over here. And I want to run this test. So in any case, the tests should pass with or without this change. And this shows how the types that consume something that consumes A are actually covariant in A. They're functors in A. It's the same thing. Let's see. Ah, it failed. All right. So that also didn't work. So let me undo that. And run the test again. Pretty sure it again compiles the first one, the first test that used the Curry-Howard library more. The Curry-Howard library is slow on those examples. All right, we're done. We're all right. So these are probably bugs or something that I could fix in the Curry-Howard library, but the important thing is for us to understand how to do this by hand, and that's what this tutorial is about. The last worked example right now is to do this. You have a bunch of Scala case classes with sealed trait. You need to identify which types are used covariantly and contravariantly, and verify that with covariance annotations. Here's how we do this. So here's the sealed trait. So I put already the covariance annotations. Now, the first thing I would do is to write this in a short notation, because this is a lot of text with names and all that in the short notation. So what do I have? The first case class has B and C. So that's A times B is this, and then B to int. The second one, the re, is A, B, and int. So that's this product. The third one, the she, is the string to A and B to A. So product of these two. And now I just look at this and figure out what types it has and whether these types are used covariantly and contravariantly. So I find that A is only used in covariant positions. So here I have an A, here I have an A, here I produce an A, here I produce an A. So those are covariant positions. To the right of the arrow, or the final arrow, or without an arrow. Now the B is used here in a covariant position, and here in a contravariant position. Here covariant, here contravariant. So that's hopeless. So B cannot be, B is neither covariant nor contravariant. Now there are other types like int. So int is used here in the covariant position, here in the covariant position. So int would be covariant. So if I wanted to parameterize this by the type of int, it would be a covariant or a functor with respect to that parameter. And the string here is used contravariantly, only in one place. So that would be a candidate for contrafunctor. If I needed to parameterize by that type, that would be a contrafunctor. So let me do that. So I changed integer to I and string to s, and then I put minus on s, plus on I, plus on a, and b is not marked because it's neither covariant nor contravariant. And now here's what would happen if I put a plus here instead of minus. So let me compile this and run this test. If I do that, the compiler will tell me that it's an error. So it will know that this s is used here in a contravariant position. IntelliJ doesn't show me the red for that, but here's the error message. Covariant type s occurs in contravariant position in type s to a of value f. So that's the error. And that concludes our worked examples for this part. And now there are some exercises of the same kind for you. So after you have done these exercises, you have an understanding of how to work with functor types. We have been checking laws of functor by hand every time by writing tests. Now this is not very satisfactory because a main question still remains here. Is it true that any data type where A is, well, a type parameter in covariant position, is it true that the data type is a functor with respect to A? And I could write any kind of stuff like this, and it would take time and effort to check the laws each time I have a type like this. But just visually, I see that here A is consumed, but the whole thing is consumed. So this is covariant usage of A. Here's covariant, and here's covariant. So the entire type is a functor with respect to A. That seems obvious. I could write an Fmap function very easily by just mapping each of these A's to B, A to B, A to B. This I map to the same integer, A to B. This I map to the same integer. This R I map to the same R. I know how to do this. We just had examples of all kinds of different types of this kind, types of this sort that we can implement as functors. But do the laws hold? And do we need to write tests every time for this kind of thing? In fact, so the way to answer this question is to realize that these data types are built from parts. They're built like from a Lego set. And what are the parts? So these are the constant types like integer or unit, and they're type parameters, and then there are operations that, for example, take two parts and put a plus between them, and you get a new type, or you use the arrow, or you use the product. So basically these are type expressions that are produced out of constant types, type parameters, and these operations. Or you can have also other operations like composition of functors, like you take one functor and apply it to another, like we did with our examples. We took an either, and under the either we had some data types that we defined and so on. So that's a composition of functors, or type constructors. And we have noticed that every time that some type is moved to the left of an arrow, its covariance is reversed. So this would be contravariant in A, and this is again covariant in A. And so does this intuition always work? Or are there some cases when this is wrong, that this is not the right functor, or the laws don't hold? And also note that if we don't use the function arrow, then everything is going to be always covariant. So if we have a function arrow, then we have to trace which one is covariant. But if there's no arrow, if a type was made without using the arrow operation on types, then all positions are covariant. And so these are types that are called before polynomial types, or polynomial type constructors. And if this intuition is correct, then they're always functors. So all polynomial type constructors are functors. And to answer this question, we're going to build Fmap incrementally as we build up the type expression out of these parts and operations. And at every step, when we take, for example, two parts and put them together, we define what the Fmap is for the new type constructor, and we check the law that holds at that step. And once we go through all possible steps, which are only 4, as far as I can see here, then we're done. We will have proved by induction that any type constructed from these operations will be a functor. So let's see how that works. So the building blocks for functors are constant functors and identity functors. So what does that mean? The constant functor is a type constructor that takes a type parameter A and always returns the type C. So, for example, int can be considered as a functor that is parameterized by some A and always has a type int. Not a very interesting functor, of course, but nevertheless a valid functor if you take Fmap, which is always equal to identity. So the value of type C is never changed. And interestingly enough, this is a contrafunctor at the same time, with the contramap also equal to identity. And all the laws hold trivially, because it's always identity. So all the compositions are always identities. So that's not much to check. The identity functor is the functor that takes a type parameter and always returns that same type parameter. Now, notice how I started to use terminology that the functor takes a type and returns a type, as if functor is a function on types. So that's indeed the case. So you can consider functors or type constructors as functions of types, functions that take types and return other types. So that's, in Scala, it is noted, it is very clear that this is the case because we use square brackets to denote type applications. So this is very similar in exactly almost like having a function f that is applied to a type, which is a function g applied to type A. Now it's type level function, the function that takes types and returns types. So these are type constructors. So it is a good way of thinking about type constructors, just functions in the type space. So the Fmap for the identity functor takes the f and returns the same f. So it means that if you want to transform A to B, then you just apply the same f to A and you get a B. the laws hold in a very easy way. Obviously, if f is identity, then this is identity, and composition is composition because we haven't changed anything. So f is unchanged. Now, the operations of creating new functors out of previous ones is what we're going to be concerned with next. So imagine we have some functors f and g, and we already have the Fmap implementations for them, and we already checked the laws. So f and g are functors, and we already checked that. And now we need to build a functor such as this one. So we need to build a new Fmap, and we need to show that the laws hold for it. And then we need to show, therefore, that this type constructor is a functor. And we do the same for these, for this. And also, well, we can see how that works because we already have experience in examples implementing Fmap for various constructions like this. So for example, this is just built by pattern matching, and we preserve the left side to the left and the right side to the right. And here we tuple the two results and again preserve the order. And here we substitute the function argument into Fmap. Remember that trick? We have g goes to f of x of whatever g. So that's the kind of trick we need to do here. An interesting thing in this case is that for this construction to work, f must be a contrafunctor and g must be a functor. So then the contrafunctor f will be in a contravariant position, and the result of this will be covariant in A in every place. Now this, when you do composition of functors, then you compose the two Fmaps. You just do Fmap here, and then you do Fmap of that. And the final case that is interesting is type recursion. So type recursion means that you define a type f using a recursive equation. So you have some r, which is a functor. In both a and x, it must be a functor. And then you write this equation. So remember what we had as an example of recursive polynomial type. So we wrote this equation. So actually this equation can be written as LPA equals some functor applied to LPA and A, because this is a type construction of the same kind as we are considering here. And so this can be just parametrized like this, and then this is a recursive equation because we're using FA inside here to define itself. And we can then define Fmap for this, just like we did before in that example. And the Fmap function will be recursive, and we'll use the Fmaps of this functor. So that is all the operations that we need. So for contrafunctors with appropriate changes, we will have exactly the same constructions, except that here, this should be a functor, this should be a contrafunctor, then the result is a contrafunctor. So what remains is to check that in each case, the functor laws still hold after each operation. So let me check this for a few cases, and I will leave other cases as exercises. The first case is the disjunction of two functors. So how does that work? Now, let me actually go and show you the code for this disjunction before we look at the short notation. So in this code, what I'm doing is I define two functors in some random way. For example, f1 is just a tuple of a and integer, and f2 is an either of integer to a and a. So you see this is a is covariant and covariant here. So I define these two functors. I have defined some helper functions to help me check laws and so on, but just ignore it. There are these Fmap classes that I defined in the tests. This is not essential. The essential is that we define the Fmap of the right type, and here I use implement because it just works. And I need to define the equal function for F2. So, but suppose I'm given F1 and F2. So how do I define a disjunction? Well, first of all, I need to define the data type. Data with parameter A. So again, I call this data just to be consistent with all other examples. But this is just a name for this type. So this is an either of F1 of A and F2 of A. So you see, in this case, we just use an either, and we don't need an extra case class to wrap this in. And I define the Fmap. So how do I define it? I use the two Fmaps from the previous functors. So these are the classes that I define. They have this .code method that represents the code of the Fmap. And this is necessary for type reasons, but not necessarily the best way of doing the functor constructions. That will be sufficient for now. So I define, how do I define this Fmap? Well, the data is a disjunction of functor F1 and functor F2. So I need to match on this disjunction. So I match when I'm in the left, then I also return the left. I'm supposed to return, so I need to return the left part for the left and the right part for the right. So this is the code that needs to be written for that purpose. Note that this code does not use any details about what these functors are. It just uses the Fmap for them. So I have the Fmap1 and Fmap2 for the functors F1 and F2, and I just call these Fmaps on the data that I have. So that's how it works, and then I check the laws of identity and composition. But can I understand why these laws hold? I mean, they do hold. The tests pass, but I want to have understanding and assurance that this is really correct for all functors, not just for particular functors I have chosen. And this is what I would do. I would reason about the code more generally, and I would use the short notation for the code to make it easier. So assume that FA and GA are type constructors for which we already have the Fmap, Fmap F and Fmap G, and we already know that the laws hold for them. Now we define the Fmap for the functor F plus G, or would-be functor F plus G. Define it like this. So the data is a disjunction of P and Q, and P is of type FA and Q is of type GA. So this is our either from the code. And this is the argument of this function, and the result is a disjunction of left and right corresponding to P and Q. So exactly what the code was doing, I just wrote this in the short notation. And in the short notation, P is here, and so if P is given, then we return this plus 0, and if Q is given, then we return 0 plus that. So that corresponds in the code to returning left or returning right. And that's just the short notation that I use to reason about these laws. Let us check the laws. We have defined the function Fmap F plus G. Let's check that the laws hold for it. Now, first law is identity law. If f is identity, then fmap f plus g of identity must be identity. And we assume that the law holds also for, already holds for f and g, fmaps. So this is a quick check then. P plus q is an arbitrary value of type f plus g. And then by the formula, we need to apply fmap of f to the p, which is identity. And we need to apply fmap of g to the fmap g of f to the q, which is again, and that is again identity. So we just have p plus q. So we take p plus q, we return p plus q. And that's obviously identity. So identity law holds for fmap, f plus g. The composition law is a little longer to check. But note, as we noted in the code, we don't actually use the structure of the functors f and g. We just use the fact that they're functors and that fmaps for them work correctly. So the composition of these two fmaps, let's decompose first. So we need to first apply f1 and then f2. So when we apply f1, then we have this. This is a definition of our fmap f plus g. And then we apply that, and then gives us the two compositions in the left and in the right. And then we can simplify that using the law for f into this, using the law of g into that. And that's exactly the same as if we have applied our fmap f plus g to the composition of functions f1 and f2. So I suggest you go through this computation yourself and check that for any p and q that you give here, for any, or rather not for any p and q, for any value of p plus q, because there's only p or there's only q in that disjunction. So for any p plus q, you always return exactly this. So the law holds. And the law holds precisely because this fmap f plus g was defined to work, it was defined here, to work separately on p and on q and to return corresponding parts of the disjunction. If we mixed up somehow some of these parts, so for instance, we're given p, but we return the right part of the disjunction sometimes, that law would not hold. Because the law, obviously here, it depends on having the two parts completely separate. So that concludes the proof that this construction gives you a functor if the f and g are functors. The next example is to show that if f is a contrafunctor and g is a functor, then the function from g to f is itself a functor. So let me go to the code which I have for this. So I have some contrafunctor, very simple one. And its fmap is so simple that it can be automatically implemented. I define equality for it as necessary for the test. And then I define this data as a type. I don't want to have an extra case class for extra complexity. And this is just defined like that. So exactly the same as the formula for the type. And I define fmap. So how do I define fmap? Well, this seems to be a lot of code, but actually this is just a definition of types for clarity. I have an argument f of this type, an argument dA, which is data A, and an argument cf1b, which is part of data b. So data b is cf1 of b going to f2 of b. So it's a function that takes cf1 of b as an argument, so I have to return that function. So that's how I'm returning it. And the result must be f2 of a. So all this must be f2 of a. So how do I make this work? I use f2 of b, not of a, f2 of b. the only way to get f2 of b is to apply something to f2 of a, because I cannot just construct f2 of b here from nothing, from scratch. I have no idea what that functor is and what b is. So I need to use the data I'm given. So I'm given this f, dA, and cf1b. So what's my plan? Well, first I'm going to map cf1b into cf1a. And that's a contrafunctor map, contrav map, because I have a to b, so I can map for the contrafunctor cf1b to cf1a. So then I have this, I put that into dA, I get f2 of a, and then I fmap with f. f2a goes to f2b, f2 of b. So that's the whole thing. I put the contra map for contrafunctor 1 into here, apply this to cf1b, I get a cf1a. I put that as an argument into dA, I get a f2a, and then I use fmap2, which is for f2, again with the same f, on the result. And the laws hold. Why do they hold? Let's prove that they hold in general. Because in the tests, we only have specific contrafunctor and specific functor, and specific types even. We cannot just run tests for generic functor. So let's prove mathematically that this is true. It's a very similar proof to the previous one. The details are a bit different. So here it will help if we have some shorter notations, definitions. So instead of fmap g of f, I would just write gamma f. Instead of contramap f of f, I would write phi of f, phi f. So phi for f and gamma for g. I'm just replacing Latin letters with Greek ones. So this is the code that we had in our Scala example written in this notation. Takes q, first uses the contramap of f on q, puts that into p, which is this, and then uses the map gamma, gamma f on that p. So then we check the identity law, we just substitute these expressions. So we take an arbitrary p of this type, which is now our new functor to be, and then we use, we just substitute, we get q goes to p of q, right? Because gamma is identity, phi is identity, so it's q going to p of q right here. Now q going to p of q is the same as p, because this is a function that takes some argument and applies p to that same argument. It's the same as what p would do by itself. So this expression is exactly the same as this expression in its effect. So that concludes the proof of the identity law. We showed that fmap of identity applied to some p gives you exactly the same p. The composition law is checked like this. So we assume that the composition law already holds for phi and gamma. And here we see opposite order of composition for phi because it's a contrafunctor. So then we apply the definition and we get, first we apply fmap fg of f1. So first we apply this, and that's this gamma f1 p phi q. And we put that in there, apply again, and we have a curious thing that we have gammas together and phi's together when we do this computation. Because here, instead of p, you have to put in that definition. This q goes to this. So when you do that, the gamma is next to the gamma and the phi is next to the phi. So now those are compositions of gammas, so we can use the composition law that already holds for gamma and replace this by this, and also for phi. Note the order. So for gamma is this order, for phi is the reversed order. And this is therefore exactly the same as what we would have if we apply the new Fmap to the composition of functions f1 and f2. So then we have proved the composition law. Note that the order of the compositions must be reversed for phi, otherwise this thing just won't work. So if phi did not have this reversed order here in this composition, the proof would not go through. So this won't work if f is a functor. F must be a contrafunctor, which is what we expected from intuition. From our intuition, whatever is on the left has reversed its covariance. And so if this is a contrafunctor, if this were a functor, then being on the left makes this whole thing a contravariant in A, and that's wrong for the functor. So this is our intuition. This intuition is correct, as we have just shown. Contrafunctor behind the arrow, or to the left of the arrow, becomes covariant, and vice versa. Here are some exercises for you to check that this works, and to check that this works for contrafunctor G and functor F. So this is quite similar, but the opposite order. And also to show that this is neither a functor nor contrafunctor when they're both functors or both contrafunctors. So that's much easier because you just give an example and show that the types don't match. So to conclude this tutorial, I would make a note that this kind of code is certainly not the best way of dealing with functor constructions. So if you want in your code to construct new functors like this, I would suggest taking a look at the libraries that do this. There are two main libraries, Scala Z and Cats. So these libraries include functionality functionality that is quite similar to what we're doing here. They can deal with functors generally. So the power of functional programming languages such as Scala and Haskell is that you can write code that takes an arbitrary functor and transforms it in some way. So you can, not only as we have done, we parameterize code by types, but you can also parameterize code by a type constructor. So you can have a function, which I did not show here because it's quite advanced stuff, but you can have a function that is parameterized by these things. So it would work for any f1 and f2 with certain properties, and that's the power of these type systems, which is not present in most programming languages. So in Scala, this is a little difficult to write and quite abstract if you try to write it from scratch. So these libraries help, and they can define functors and help you write code with functors. So for instance, if you wanted to have code that does something for any functor, then I would suggest you try it yourself, but it would be a bit hard. Explore these libraries. Also, there's a library called Shapeless, which has some utilities for automatic construction of functors. So you see, as you have noticed, these operations are quite mechanical. So there's no choice here. And all this can be done automatically by some preprocessor or the compiler of Scala. So there are libraries that allow you to write code to automatically implement Fmap for your own types with no code that you have to write, or almost no code that you have to write. Because all these operations are dictated by the mathematical properties of functor. There's no choice The Curry-Howard library can help in certain cases, but it doesn't know that you are constructing a functor instance. It does not check the laws. So if that is your purpose, you should try to explore these libraries that allow you to automatically construct a functor implementation for your types. And any types of this kind, I think, should be supported. If not, make a PR for them. Well, this concludes the tutorial.